In this video, I'll be working through some sample problems to find work done and to apply the work energy theorem. All of the example problems in this video come from the G & Colley Physics 6th edition textbook. In our first scenario, we're looking at work being done on a crate. A person pulls a 50 kilogram crate 40 metres along a horizontal floor by a constant force of 100 newtons. This acts at a 37-degree angle, and the floor exerts a friction force of 50 newtons. We want to calculate the work done by each force acting on the crate. The first thing I'm going to do is draw a diagram of the scenario just to visualize what's actually happening. So I've got my 50 kilo crate being dragged by a person. I'll give that a bit more of an angle. I'll make them a taller person. There we go. So this is force applied at a 37-degree angle. We've got the mass of the crate. It is being dragged a distance of 40 meters. The pull force is 100 newtons. And the frictional force is 50 newtons. Okay, we're being asked to determine the work done by each of the forces that's acting on the crate. So I want to draw now a free body diagram to help me wrap my head around all of the forces that are being applied. So I've got my pull force, which is 100 newtons. Something I forgot to do as well actually was I'll define this as the positive direction to the right of the page as the positive direction. So my frictional force is going to take on a negative value. I'm going to have normal force, and I'm going to have force due to mass times gravity. And those are going to be equal to one another because we know that the crate's not flying up into the air or falling through the floor. So I'll list my givens now. I've got a mass of 50 kilos. I've got distance 40 meters at an angle of 37 degrees. My frictional force is negative 50 newtons, and my pull force is 100 newtons. So now I want to determine the work done by each of the forces that's acting on the crate. So I'm interested in my normal force, my force due to mass times gravity, my pull force, and my frictional force in turn. So when I apply my formula for work done, it's work done by a particular force. So I want to define that. So my general equation is going to be work is equal to force times the distance times the angle that the force is applied. So if I am I'll look at normal force first. So work done by the normal force is equal to the normal force multiplied by the distance travelled. Well, the distance travelled is equal to 0 meters. As I said, the crate's not flying up into the air. It's not going in an upwards direction. So if distance is equal to 0, then the work being done is also equal to 0, the work being done by the normal force. And I can say the same thing about work being done by mass times gravity. The crate isn't falling through the floor. which means that the distance travelled is 0, which means that the work being done is also equal to 0. When I have a look at my work being done by the pull force, I can substitute my values in. And that will give me 3,200 newtons of work being done by the pull force. And lucky last, work being done by frictional force. Remembering my frictional force has a negative value. That will give me approximately negative 2,000 newtons. Okay, and in this example, we're really just applying the two formulas, the one to calculate kinetic energy and the work energy theorem. It's very straightforward here. So a 145 gram baseball is thrown to acquire a speed of 25 meters per second. In the first part of the question, we're asked to find its kinetic energy, and then we're asked to find the net work done on the ball if it started at rest. So I'm going to list my knowns. I know that the mass is equal to 145 grams, and I'm straight away going to convert that into kilograms. I'm told that its final velocity is 25 meters per second, and I know that its initial velocity down here, it started at rest, that's going to be equal to 0 meters per second. So to calculate its kinetic energy, pretty straightforward. I just plug these values straight into the equation to find kinetic energy. Half mass times velocity squared, so half times 0.145 times 25 squared. And that gives me a value of 45 joules. And for part B, I'm just applying the work energy theorem. So the net work is equal to the final kinetic energy minus the initial kinetic energy. Now we're told that the ball started at rest, which means that its initial kinetic energy is going to be equal to 0, which means that the net work done is equal to the final kinetic energy, which we just calculated up here. So that is also equal to 45 joules. And our last example is finding net work for an accelerating object. So fortunately for us in this scenario, we're actually given a diagram. I won't need to draw one out, so I can start off by listing my givens. So how much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? So I know the mass of the object. I know that its initial velocity was 20 meters per second. and its final velocity is 30 meters per second. And the formula I want is for net work. So I can just plug these values in straight into the formula. You want to make sure that you don't forget to square your velocity. I think that's the most common, the simplest mistake to make. So the final answer here, the answer we're given is 250,000 joules, and we want to express that in scientific notation, 2.5 times 10 to the 5 joules.